In this video, I'm going to talk all about asymptotes. So we need to start with a few preconditions here. We're going to start with a rational function, alright, and our rational function is going to be r of x. Right? R of x as a rational function by definition is made up of two polynomials, one in the numerator, one in the denominator. Alright, so we'll use p of x for the numerator and q of x for the denominator, so we have to put the condition on q of x that it's not 0. Now by not 0 I don't mean that it can never equal 0, I simply mean that it is not the 0 polynomial. Right? And then lastly here I need r of x to be in lowest terms, that is no common factors between the numerator and the denominator. Right? Once I've done this, I've got a nice rational function, we can start talking about asymptotes. So the first type of asymptotes I'm going to talk about are vertical asymptotes. Alright, now vertical asymptotes are values of x where the denominator is equal to 0. Alright, so essentially where r of x is undefined. So if I take a function here, let's say I take r of x to be 2 over x minus 1. Alright, so now I have to ask myself, where is 2 over x minus 1 undefined? Well, it's undefined where the denominator is 0. So it's undefined where x minus 1 equals 0, which is going to happen at x equals 1. Alright, so I have this point where the function's undefined, so on my graph I have a value of x that the graph can never obtain. Right? So if I look, I'll start to do a quick sketch here. That's not a very good straight line, is it? Alright, let's see if I can make an actual straight line here. That's a little better. Alright, at 1, I know the function can never take on that value. So what I have is a wall. Okay, I have this wall that goes through x equals 1. That my function, the graph of my function, can never cross. Right? I'm not saying it doesn't exist on both sides, it will, but essentially to get from this side to this side it has to jump over that line. It can't actually cross that line. So what I want to look at is what the behavior of the function is. So I'm going to take a point here, take the point 2. Alright, what is the value of the function at x equals 2? Well, that's going to be 2 over 2 minus 1, which is going to be 2 again. So if I come up here, say 2, then I have this point right here that's on the graph of the function. So what I want to look at now is what is the behavior of the function as I approach this line. Alright, because I can get close to it, I just can't touch it or cross it. Alright, now you can verify this using the table function on your calculators. But what's going to happen is I'm going to get closer and closer and closer, and I'm going to keep getting closer and closer and closer. I'm never going to touch it. I'm just going to keep going up, getting infinitely close to that line, right, on that side. Alright, so what this is telling me is that as x approaches 1, the asymptote from the right-hand side, what happens to f of x? Well, f of x approaches positive infinity. Alright, because as I get closer and closer to this line, the value of my function just gets larger and larger and larger. Alright, now let's look at the other side. Suppose I take 0. Right? If I take x equals 0 and I plug it into this function, I get 2 over negative 1, so I get negative 2. And so there's negative 2, right, which means that's a point on the function. Now again, if I look at what happens, just take out your calculator and do a table. Look at what happens as I approach 2. I get closer and closer to, I approach 1 rather, get closer and closer to 1. Alright, what's going to happen is the function is going to get closer and closer, but it's never going to touch and it's never going to cross. So as x approaches 1 from the left, f of x is just going to shoot down. It's going to approach negative infinity. Alright, so the behavior at a vertical asymptote is going to cause the function to either go up to positive infinity or down to negative infinity. And that, again, if you think about what happens to the function here, as I get close to -1 from the right-hand side, x is getting infinitely large, which means my denominator is getting infinitely large. And when you take a constant and divide it by something that's infinitely large, no, I get closer and closer to 1. I'm sorry, this is the function that's getting infinitely large. So I get closer and closer to 1, the denominator gets closer and closer to 0. So as the denominator gets closer and closer to 0, the value of the function gets infinitely large. That's what I was trying to say. Okay? All right, and that's true again from the left. So that's the behavior at a vertical asymptote. The function is going to go to infinity, either positive or negative. All right, so that's our first type of asymptote. Our next asymptote is what's called a horizontal asymptote. All right, now a horizontal asymptote, while the behavior is similar, it's still a line that the function's going to approach. It's not exactly the same. All right, so the behavior, here is this. All right, we're looking at the behavior of the function r of x as x approaches infinity. All right, both positive and negative infinity. All right, so let's take our r of x, the one that we've been working with, right, 2 over x minus 1. And let's see what happens, all right, as x approaches positive infinity. Let's see what r of x is going to do. All right, well, if x gets infinitely large, then the denominator is getting infinitely large. And if the denominator is getting infinitely large, when you take a constant and divide it by something that's very large, the fraction gets very small. All right, so what's happening here is we're taking a constant and dividing it by something that's infinitely large, which means my function is getting infinitely small. It's getting closer and closer to 0. The same thing is true as you go to negative infinity. All right, if my denominator gets infinitely large in the negative side, all right, then the fraction is getting infinitely small in the negative side, so it is also approaching 0. All right, so the behavior of this particular function, right, and if I go back to my graph, all right, now I can look at what's happening over here, right? As x gets infinitely large, what's happening to the function? Well, the function is getting closer and closer to 0 on that side. And as the function gets infinitely large in the negative direction, the same thing happens over here. The function gets closer and closer to 0, all right, but it never actually crosses it. Okay, so our horizontal asymptotes, this is a particular case. So we have kind of a general case, all right, and the condition, our condition for a horizontal asymptote is that the degree of p of x, the numerator, is going to be less than or equal to the degree of q of x, our denominator. All right, this implies a horizontal asymptote. All right, so less than or equal to. So if the degree of p of x, is strictly less than the degree of q of x, like it is here in our example function, then the horizontal asymptote, I'm going to abbreviate that here, is going to be x equals, horizontal is y, is going to be y equals 0. Right? anytime the degree of the numerator is less than the degree of the denominator, the horizontal asymptote is the x-axis, y equals 0. Okay? Now, if the degree of p of x is equal to the degree of q of x, then the horizontal asymptote is going to be the ratio of the leading coefficients. Alright, now what do I mean by that? Let me write it down first. Now, what do I mean by that? Well, suppose we have an r of x, right, a rational function that is, let's say, 2x squared plus 3x minus 1, and make the denominator 3x squared plus 4x minus 2. Alright, so I have this rational function. The degree on top is the same as the degree on the bottom. And okay, rather than trying to be all professional and edit this together, I'm just going to say, alright, sorry, I'm back after a small coughing fit. So where were we? I'm looking at a rational expression here, rational function, where the degree of the numerator is the same as the degree of the denominator. Right? So in a case like this, to get my horizontal asymptote, what I'm going to do is I'm going to look at the fraction that's made up of the leading coefficients. So in this case, y equals 2/3 is my horizontal asymptote. Alright, so I'm not going to try and sketch this or even try and give you an idea what it looks like. Okay, but basically this is simply a case for right now, until you have some calculus behind you, of remembering the difference between the two of these. If the degree of p of x is less than the degree of q of x, y equals 0 is your asymptote. If the degree of p of x is the same as the degree of q of x, then y equals the ratio of the leading coefficients is your horizontal asymptote. Alright, now just a quick little note about the behavior of functions and horizontal asymptotes. Where a function cannot ever cross a vertical asymptote, it can cross a horizontal asymptote. Remember, the idea here is we're looking at the behavior as x approaches infinity. Right? So for finite values of x, it's possible for x to cross its horizontal asymptote. In fact, it can cross it many times, as long as eventually the behavior settles down. There is a point after which it no longer crosses the asymptote, but approaches it. So just real quick visual here. Alright, if I have, let's say, y equals 0 is my horizontal asymptote for this imaginary function, I can have this function cross. In fact, it can cross lots and lots of times, as long as eventually it settles down and starts approaching. Alright, so there's a point after which this function becomes asymptotic to the x-axis. Alright, so that is one difference between horizontal asymptotes and vertical asymptotes. Alright, so let's move on to our third type here, which are called oblique asymptotes. And for oblique asymptotes, I'm going to restate our definitions for r of x because they're a little bit more important here. Alright, again, we have this rational function, and in particular, this is very important, r of x is in lowest terms. Okay, so the situation here is the degree of p of x, the numerator, is going to be greater than the degree of q of x, the denominator. Alright, so that's our condition. And if this is met, then we have an oblique asymptote. Now we find an oblique asymptote, right? You find one of these by dividing Alright, so you can refer yourself back to the video on polynomial long division for the details if you need a refresher. But let's say here I have a rational function, and we're going to say that this rational function is 8x to the third plus 10x squared minus x plus 3 on top. That's the numerator. And then the denominator is 2x squared minus x minus 1. Alright, so the first thing you can note here is that the degree of the numerator is 3 and the degree of the denominator is 2. So this fits our conditions to test for an oblique asymptote. Alright, so I have to divide, which means I have to divide 2x squared minus x minus 1 into 8x to the third plus 10x squared minus x plus 3. Alright, so to do the long division I have to take 8x to the third and divide it by 2x squared. When I do that I get 4x. And then I multiply 4x times 2x squared, 8x to the third, 4x times x minus 4x squared, and 4x times negative 1, so that's minus 4x. And then I subtract. Alright, so I subtract 8x to the third minus 8x to the third, I get 0. 10x squared minus a negative 4x squared, so that's plus, so that's 14x squared. And then x minus a negative 4x, so that's plus, so that's plus 3x. And then bring down the plus 3 from up there. And then I try to divide again, so 14x squared divided by 2x squared, I can do that. Right, that's 7. Multiply 14x squared. 7 times minus x is minus 7x. And 7 times minus 1 is minus 7. And again I subtract. So I get 0 there, that's good. 3x minus a negative 7x, that's plus, so that's 10x. 3 minus a negative 7 again, that's plus, so that's 10. I look to see if I can do this again, and I've got 10x divided by 2x squared, so I can't do it again. So that's my remainder. 10, that's a 10. 10. 10x plus 10, I don't really care what that is, over 2x squared minus x minus 1. And then I look at what happens to the remainder as x goes to infinity, because remember that's what we're looking at, right? So as x goes to infinity, the degree of the numerator is less than the degree of the denominator, so this whole thing goes to 0. Okay, so what I'm left with is an oblique asymptote of y equals 4x plus 7. Okay, so just in general what that would look like, just because it's kind of a strange asymptote, right? So you've got a situation here where you've got, alright, so let's make that 7. Right, there's my y-intercept over 4 over 1. So I'll have an asymptote that's going, again, like this, at an angle. Alright, that's not the only thing that's going on with this function. I also have 2 vertical asymptotes. I'm not gonna solve the whole thing out, but let's just say I've got one here like this, and I've got one somewhere over here like this. And what's happening with this is the function is behaving, right? Here's the vertical asymptote, so it's coming down, but then it hits this, and it bounces back up again. Alright, and the same thing here. Here's the vertical asymptote, so I'm coming in this way, and then I hit that, and I go back out that way again. Alright, And then it's doing something else in here. I'm not sure what the, so it'd be 3. Alright, so somewhere over here it would cross, no, somewhere over here it would cross the y-axis. So it's probably doing something like this on this side and something like this on this side. Alright, so notice that oblique asymptotes behave similar to horizontal asymptotes in that it's possible for the function to cross at an oblique asymptote. You can actually put this one on your graphing calculators and check it out. Okay, so we looked at 3 different types of asymptotes. Vertical asymptotes. All right, as you approach a vertical asymptote, the function is going to go to infinity. And then we had horizontal asymptotes, which is what happens as x goes to infinity, what happens to the function. All right. It's possible to cross a vertical asymptote. And then oblique asymptotes, which behave like horizontal asymptotes in that you can cross them. It's a little more complicated to find them. Okay. And that is it.